So very good afternoon to everyone. So let's start the week four's problem solving session. So these were majorly the topics covered in the week four by Professor Sankaran. So he started with the electrostatic electrostatic lenses, then followed by electromagnetic lenses, then majorly like basics of the SEM were covered, like resolution, magnification, depth of field, and aberration also, and how to correct them, and then some briefing about the thermoionic and field emission guns. Then electromagnetic lenses also he covered, and then last one will be covered later. So this is the this has already been covered in just a briefing session for the theoretical part. Uh, this is the this the depicts the SEM, the different parts and components of the SEM, and different like ones. So these so the left part shows the different parts like condenser lenses, two condenser lenses, 1 and 2, and then there are the objective lenses, then the STM detector. We haven't like discussed in the, but it's the still the basics, and then also the different signals like secondary electrons, auger electrons, X-rays, coherent elastic scatter, direct beam, which is used in TEM, and then incoherent elastic scattered, and the formation and formation and all have already been discussed in the theoretical classes. And further, there is like presence of high vacuum is required, and then different application part were also been discussed, environmental condition for ESEM, biological and polymeric samples, like how to prepare them and all, etc. have also been discussed. Now, if we talk about the basic working of the SEM, this is just a briefing. For detailed, you should watch the lectures. Like, firstly, there is an electron gun here, like this electron gun, and generally it comes around 1 to 30 kilovolts. So, and then so someone asked some question. Like, 1 second, let me see. So So there are many reasons we can say, suppose if it's like your filament is one of the reason is that if your filament says not in not there is not no vacuum, suppose it is like oxygen is present or basic atmosphere is present, then a filament will burn out, like we can say your light bulb, like uh, if you open it, like generally the filament will burn out. So one of the reason is that, and also if you the air will be present, then your the electrons would also collide with your gas molecules, and probably they won't reach your sample. So how will you be doing the imaging part? So generally that's these are the some of the reasons like why the vacuum are required. There may be some other reasons also. Okay, I hope I was able to clear it out. Okay. And okay, so and then after the electron gun, like the other parts are like that, the electromagnetic lenses, which can be of metallic and ceramic, then the focused electron beam onto the sample around 20 to 30 kVs. Then there comes the scan coils for doing the raster scan of the electrons or beam over the specimen. Then for like biological specimen, polymeric specimen, etc. So generally, while doing the SEM, it is one major thing is that your EST values, that is your voltage values, like for suppose you are doing for polymeric samples and all, then your voltage should be less than 10 kV. Sometimes we even go to 5 kV also. And similarly for the powder samples also, the voltage is generally less than 10 kV. However, for the metallic samples, the applied voltage is around 20 kV. The reason has already been covered in the lectures, just a briefing. And then also for the TAM part, I will be discussing in the when the TAM will be discussed. So I'm just leaving this. Uh, and then besides this, like the scan coils, and then the aperture, and then your specimen. One sec. The specimen is like image. So first, further, one important thing was in the last lecture, four important parameters like your electron probe diameter, electron probe current, electron probe convergence, and electron beam accelerating voltage were discussed. Like these were the four major parameters, uh, on which your magnification, imaging, surface morphology, and everything depends on. These are very important parameters, and one should know what are these parameters. I think this is the repeat. So now, if we talk about the signals in the SEM, so there are like secondary electrons, which is generally for the imaging part, and then there is second one is the backscattered electron BSE, and then third one is the characteristics X-rays, like for the elemental mapping of EDS and wavelength dispersive spectroscopy. And then their applications have also been discussed, like for the BSc, like if you want to see the contrast, then generally we go for the BSc imaging. And then if we do generally for the and if we simply want to do the topographical analysis, then we go for the second electron. Now second electron also are different types, which I will be discussing later on. And then if we talk about the EDS and WDS, then if your composition is less than 10 weight percent, then around 10 weight percent, then we'll go for the EDS. And then if it around 1 weight percent, then we go for the WS. So then secondary electrons typically have energy less than around 50 electron volts. And then your high energy primary electrons, or the whether the elastic interaction with the nucleus takes place in the backscattered electron, while the inelastic interaction with your electron cloud on the loosely bound outer shell is take place in the secondary electron. So this is basically the difference between your BSc and the secondary electron. So uh, and then comes the different types of secondary electron, SC1, SC2, and SC3. So this is the mechanism for the SC1. So here they are the incident electron beam knocks off an loosely bound outer shell electrons, as seen from the diagram also. Here the incident electron beam is knocking off this secondary electron, and then the signal generated from this will be termed as SC1. And generally, as like previously discussed, the energy of this SC1 is less than 50 kV, 50 electron volts. And then you're also the yield reduces of your SC yield reduces as the depth of your sample increases. So generally, your the SC is for topographical information. Now, if you compare it with the SC2 and SC3 images, SC2 and SC3 signals. So the SC2, if you see the paths, like here your specimen, here the electron beam comes in contact with your specimen, then here it generated SC1, and then followed by here it transmits some a little bit, and then it again comes, then SC2 and SC3 are generated. So SC2 is the primary electron you're undergoing when your primary electron undergoing scattering with your sample and manages to escape somehow, then your significant energy, however there is significant energy is lost due to the scattering phenomena taking place here. And if you talk about the SC3, your BSc electron when hitting your specimen chamber, and generally additional electrons come out, then therefore the SC1 is the most important, and generally this is used in your topographical analysis. So this is a basic uh, difference between your SC1 signal and BSc image. So the first one is your BSc, and then your second one is your SC signals. So I think in your quiz for the week 4 also there is some similar type of problem. So here when we compare these two images, it is clear that your BSc is showing a typical contrast between due to the atomic number difference between, like here it is some little bit darker, however here it is a brighter one. While the SC1 is showing a topographical analysis very clearly and very precisely, we can say. Uh, so if we BSCs are generally considered to be the electrons that exit from the specimen with your electron, like with your energy greater than 50 electron volt. It also include your Auger electron. And further, the higher is your the atomic number of a material, the more likely it is to be backscattering will occur in that case. Okay. And if we move to the this another example for the SE versus BSC. So we can clearly see like the phase in your SC image, like it is not like there is no, we can say, the topography is like clear, like, but however there is no much contrast like in different phases of the material. Like here it is clearly visible that here this is a nickel rich and this may be some alumina composite, alumina nickel composite. So similarly, like in your like problem, in your like one of your assignment, there is one gallium nitride chip is shown. So this was taken from the like e-waste problem. So generally, uh, like suppose your like electronic waste, like suppose if I am having some of your LEDs, and if I did some pyrolysis and some other treatment, then your in that sample your some char and metallic fraction will both will come. So if you want to see like whether the complete decomposition uh, or like complete incineration or some pyrolysis has been taken place, then sometimes we do BSc imaging. So there we are clearly like able to see like the some gallium nitride semiconductor chip was present in your char sample. So in that case, in that scenario, like BSc is like very useful in that. Okay, and then if we there were like and what were the other things which were taught. So let me see like then at starting, like electrostatic lenses and electromagnetic lenses were covered, and then basic difference between them was covered, which is very important. So I will read the exact line from the lectures. The difference between your light optical system or electrostatic with your electromagnetic system. So in your light optical system, your image inversion takes place. So inversion takes place at an angle of around 180 plus minus 5, and further additional rotation takes place here. So if you have like double lenses, then it's further rotated back to the same. So in that case, like this is the major difference uh, between the electrostatic or light optical system with the electromagnetic system, that the image rotation takes place. And like this is also very important in your like TEM analysis also, so which will also be covered. And what I wanted to cover, uh, so meanwhile, if you have any queries regarding what I'm like covering, so you can also like message or drop mail me also in later cases. And further, like in the SC and BSc, like there was one major difference in the detectors also. So in case of the SC and if the collector voltage is more than like positive 300 voltage, then it will allow for both SCs and BSCs. Like for minus 100 volt, only BSCs will be pass through. So this is was the one of the difference between your detectors for the SC and BSc. Okay, and then what we are also talking about. Okay. So like these were the these are the major things which were covered. So let's move to the MCQs. Some of the MCQs already been, you have, I think you have already been uh, already did from your assignment and previous assignment. So first one is that the portion of your electron current that leaves the gun through the hole in the anode is called. So anyone would like to comment, or like I think it is already solved in your problem also. So the portion of your the electron current that leaves the gun through the hole in the anode is called the beam current. So and then there is like there was in one lecture the difference between the different currents like beam current, probe current was also been taught. Like when your I mean when your like electron beams comes in contact with different your lenses and apertures, then your current significantly reduces. So it is not like that your beam current is similar to the probe current. I think you already know. So the portion of the electric current that leaves the gun through the hole in the anode is called the beam current. And the second one is that the space charge effect is minimum when, I think the space charge was covered in a quite good manner, like what is it. If anyone would like to write what is this in the text, in the comments, it would be good for someone who don't know. However, the space charge effect is minimum when your voltage is high and your beam current is low. So and then your another problem is that increasing in your working distance leads to what will be the effect of your working distance on spot size and image resolution. Anyone who would like to comment? So I think it has also been covered. And for the space service, if you talk about the space service in general, I think. So if you talk about your the so the increase in your working distance leads to larger spot size, and yeah, it degrades the image resolution. So many of you have like uh, answered correctly in the chat box. So if I was talking about the space chart, so it causes like so when near your focal point, the electrons collect and form a cloud of negative charge. Okay, so due to which there repels and repulsion, and it also limits the emission of electrons from the surface. However, at higher electron volts, it is like lesser. It still it can be minimized at higher voltage and lower beam current. Okay. So next, if you're moving to the fourth one, which of the following option is correct? Uh, so match the following. So this is from your current problem or this week's. Anyone who would like to say like or match like the secondary electrons, backscattered electron, X-rays, and Auger electrons. So if we see like if we match the secondary electron, so yeah, it is used for imaging part. Yeah, and then if we yeah, yeah, you're right. The correct answer is A. So the backscattered electrons are used for like the crystal structure, and X-rays are for the compositional analysis, and Auger electrons for the detection of very uh, light elements. Okay. Now let's moving to the next problem. So image is always rotated by a certain angle when the electron passes through an electromagnetic lens. This was the first lecture when the comparative study of the electromagnetic lenses and then the electrostatic lenses was carried out. So image is always rotated by a certain angle when the electron passes through an electromagnetic lens. Yes, it is correct. And due to the Lorentz force, electrons travel in a helical path. Yeah, that is also true. Uh, this explains the this is the correct reasoning for the statement one. So both statements are correct, and then it is also the correct explanation for the statement one. So now moving to the next problem. So for thermoionic emission, which of the statement is correct for the quality of the source? The melting point of the source should be high, and then the another one is the work function of the material should be low. So yes, the melting point of your source material should be high, and then your work function is also should be low. But these are not like explaining the correctly like the reasoning of the. So statement one and statement two are correct, but the statement two is not the correct explanation of the statement one. Okay. And then if you move to the next one, which of the following is correct for field emission guns? So FEG, like field emission gun, can work at room temperature. Yeah, this is right. And then your tip radius should be very sharp. This is also right. But there is no relation between FEG room temperature and then the tip radius. So again, D will be the correct answer. Okay, then if you move to the, if the strength of the condenser length increases the probe diameter. So anyone who can explain this, or like what is the correct answer? So this was the last lecture. It was taught in the effect of condenser length strength, length strength. So increase in your condenser length, it increases the demagnification of each lens and reduces the probe size. And further, the final probe size can only be reduced at the expense of reducing the probe current, and a conscious choice between minimizing probe size or maximizing probe current. Okay. So the correct answer will be your decreases. Okay. Now if you move to the ninth one, if we increase the condenser current, what will happen with the final probe current? This will also reduce. Okay. And which of the following option is wrong if you want to increase the brightness in an electron microscopy? So if we see that there is also one problem in the present case in this weak solution, like where we need to find out the brightness. So this formula would be utilized in that. So brightness is your current density times pi alpha square, where alpha is your convergence angle, J is your current density, which is okay. So and here D is the gun crossover diameter, and then I is your cathode emission current. So none of the above will be the correct answer. Now moving to the next, these are the simple MCQs. So what is the primary function of a SCM? Yes, to produce high resolution. Uh, so which of the following principle is utilized in SCM imaging? The transmission of electrons through a sample, reflection of electrons of the sample surface, absorption of the electrons by the sample, and the scattering of the electrons by the sample. So yes, D scattering of the electrons by the sample surface is the correct answer. And which component of the SCM is responsible for focusing the electron beam onto the specimen? So objective lens is the correct answer. Which component is responsible for focusing the electron beam onto the specimen? What is the purpose of the electron detector in an SCM? So the correct answer is to collect and amplify the signal generated by the interaction of the electron beam with the sample. And moving to the next one, which technique is often combined with SCM to provide information about the elemental composition of a sample? So EDS is the correct answer. Sometimes WDS also, you can see the differences between them. In SCM imaging, what does the term secondary electrons refer to? So electrons emitted from the specimen surface as a result of primary electron beam interactions. B, electrons transmitted, no. Transmitted, no. Electrons absorbed by the sample, no. Electrons scattered by the sample specimen, no. So A is the correct answer. What advantages does SCM offer over light microscopy when imaging specimens? Higher magnification, yes. Better resolution, yes. Greater depth of field, yes. So all of them are. So these are just the basic questions. So to so that you can Visualize it. So next one is, which of the following statement about SCM is true? It requires samples to be coated with a conductive material. Yes, this is correct. It uses visible light for imaging. No. It can only produce 2D images. No. It is primarily used for studying live biological specimen. This is one of the applications, but not primarily. So what determines the depth of field in SEM imaging? So option A is your voltage of the electron beam. No. Magnification level. No. Size of the aperture. Yes. And type of the electron detector used. Okay. So C is the most correct answer. Which of the following is not a limitation of SCM? Limited sample size. Samples must be conductive or coated with conductive material. Limited depth of field. Inability to provide elemental analysis of the specimen. So D is the correct answer. Okay. So now these are the three simple MCQs. So first one is, if an SCM operates at an accelerating voltage of 20,000 kV and the wavelength of the electron is approximately this nanometer, what is the momentum of an electron in the SCM? So we know that the momentum can be calculated from the h by lambda, where h is your Planck's constant, and then if you will be dividing, then so these three you try to solve this, but you can take a screenshot of these. I am just I'll just tell you how to solve this, and then in the next class you may tell me what are the correct answers. So momentum you can calculate by h by lambda. Second one is, a sample is analyzed using SCM and the magnification is set to 5000 times. If the actual size of a feature on the sample is 10 micrometer, what will be its apparent size in the SCM image? So here the apparent size can be calculated by your actual size divided by your magnification. So your actual size, you know that this is around 10 micrometer, and then if you magnify it by 5000, so 10 micrometer times 5000, so it will be coming in some nanometer range, so you can see. And then further, a particular feature appears around 100 pixels wide in an SCM image. If the magnification is 10,000 times and each pixel corresponds to 1 nanometer, what is the actual size of the feature? So this can be calculated by your actual size will be your pixel width times pixel size times magnification. So 100 is your pixels, number of pixels, and then 1 nanometer your 1 nanometer is corresponded by your 1 pixel. So 100 times 1 nanometer times 10,000 times is the magnification, so we'll be getting around 100 micrometer. So these were majorly the things which I wanted to cover, and if you have any doubts, feel free to discuss. Then we'll discuss and we'll try to solve this. So any problem if you are having facing in solving this week's assignment or quiz or some other doubts, we can discuss now, or in the slides which I just presented. If you have any doubt in any of the slides. Okay, then if not, then you can also mail me on the discussion forum, so I will be replying to your doubts. So these were the things which I wanted to cover in this week's tutorial. So if not, then let's wrap up the session, and we'll meet you all in the next week then. Okay. Okay, then have a good evening. Okay. So very good afternoon to everyone. So I'm Rohit Galat and I will be taking the week 11's material characterization tutorial course. So in the last day we talked about basics of the TAM and from the TAM diffraction what can we infer. So we were discussing about that in detail. So we discussed that phases and crystal structure types, crystal symmetry and space groups, orientation relationship between phases, determining growth direction, interface coherency, defect identification, example, twins, dislocations, ordering behavior of crystal structure and the site occupancy preferences. These are the things that can be determined from the TM diffraction. So like now the question comes, why the electrons only? So anyone would like to answer that? So the ability to resolve the tiny objects improves as the wavelength reduces. We already know that from the week 1 class, week 1 lecture. So let us consider the microscope objective. Okay, so these are the objects to be resolved. So distance between the D, and then this is the focal length of the lens if image plane is at a large distance, and then so then we determined that the critical angle for resolution is given by 1.22 times lambda by D. So the minimum D for which we can still resolve two objects is AC times the focal length. So D minimum is approximately F alpha AC. Then it can be written as 1.22 lambda F by D. So a good microscope objective has F by D is around 2. So with lambda around 500 nanometer, the optical microscope has a resolution of around 1 micrometer. Okay. So let's continuing on that. So the resolution of the electron microscope. So firstly, we know that the it behaves as a light as well as a matter. So behaving like light, it can be as h by lambda. Matter also it can written as, so, and P is E by capital E by C. Then energy can be given as hc by lambda, and for if you consider it as a matter, then energy can be written as h square by 2m lambda square. So the for the wave behaviors, images and diffraction patterns, wavelength can be turned by energies, and for the charged particle behavior, strong electron specimen interaction, then the chemical analysis is possible. Okay. So like typically electron beam current in TEM is around 0.1 to 1 microampere, which corresponds to 10 to the power 12 electrons passing through the specimen plane. So with around 100 kilo electron volt energy, these electrons travel at about 0.5 C, approximately 1.6 times 10 to the power 8. So they are separated by 0.16 centimeter. This means that there is never more than one electron in the specimen at any one time. And further, the electron diffraction and interference occur, both of which are wave phenomena and imply interaction between the different electron beams. Now for the fundamental constant and definition, we talk more about the electrons. So the charge is given by 1.6 times 10 to the power minus 19. 1 electron volt is around 1.602 times 10 to the power minus 19 joule. So the rest mass is around 9.1 and 10 to the minus 31. Then the rest energy can be calculated and followed by the kinetic energy. The Planck's constant we know, then 1 ampere. So the speed of light in vacuum is around this. Okay, so the de Broglie wavelength of an electron can be given as lambda is h by p, and then the relation between the electron's wavelength and its kinetic energy E. So P and E are related through the classical formula, we know that. So E is given by P square by 2m, where Me is 9.11 times 10 to the power minus 31 kg, and energy can be given as h square by 2m lambda square. So h is 4.14 times 10 to the power minus 15 electron volt second, and we can calculate E as 1.505 eV nanometer square by lambda square. So don't confuse this with for energy of photons, which is given by 1240 eV by lambda. And for electrons, it is given by 1.505 eV nanometer square by lambda square. So let's solve an example. So we wish to observe a virus with a diameter of 20 nanometer, which is much too small to observe with an optical microscope. So calculate the voltage required to produce an electron de Broglie wavelength suitable for studying this virus with a resolution of d minimum around 2 nanometer. The f number for an electron microscope is quite large, so f by d is around 100. So try to solve this and we will discuss about it. So we can solve it by d minimum is 1.22 times lambda f by d, and then we can so we find out that the lambda is around 0.0164 nanometer, and similarly we can we can calculate energy as 5.6 kilo electron volt. So that means to accelerate an electron to an energy of 5.6 kilo electron volt requires around 5.6 kilovolts. Now there is one more thing like I want to cover. So we discussed briefly about the SAED pattern in the last class. So we'll discuss about indexing SAED patterns. So firstly we select the central spot. After selecting the central spot, we measure the distance between central spot and other nearest spots. This gives the uh, So so this gives the inverse of the d spacing, 1 by d for a particular HKL. Now take the ratio of the distance measured. Compare the measured ratio with the expected from the table 1 given below. Now start giving the indexes for matching ratios as given in the table. Now cross-checking the indexing by measuring the angle between vectors joining the central spot and the other spots using the following equation. Now find the zone axis using any of the two indexed HKL, and then make sure that all the indexed HKL satisfy the zone law. Okay, so here I summarized for in table for all the details for you. So like these are the some examples, simplified examples for you. So pattern 1, pattern 2, pattern 3 and pattern 4, and then these other, so you can all try these, and you can, if you